Alright, we're going to go over section 7.3 in this video. Now in 7.2, one of the main results was the Van Hoff formula, which basically says that you can, by applying a pressure, a certain pressure, you can hold osmosis off or stop osmosis. Without that pressure, there will be osmotic flow. And that Van Hoff equation just basically said the equilibrium pressure, whatever pressure you need to apply to stop that flow, is proportional to the thermal energy and the concentration. Okay, so that was the previous stuff. So our question in this one is, there's a force. There's got to be a force. Okay, so the flow, it will only flow if there is a force pushing on something. And the question is, where's that coming from? So if we look in this picture here, let's suppose we have a vertical tube with a semi-permeable membrane in a bath of pure water, and inside is a concentration of some soluble molecule. And there's a float on it sitting on top of the water and a little weight. And according to osmosis, the water will flow into here through that osmotic force, and it will lift that weight. So it's pushing on that somehow. Okay, so the question is, what's doing the pushing? This water is being pushed up, which is therefore lifting that weight. But what's pushing the water up? There's got to be a force. And so if you think about something's pushing the water up, that means the water's got to be pushing down on something by the third law, Newton's third law. And what it points to is it's the membrane. The membrane is what is actually pushing. And so the goal of this section is to see how the force from the membrane pushing on the fluid is what is giving us that our osmotic flow, and ultimately, when it's in equilibrium, the Van Hoff equation. Okay, so that's going to be our goal today. So we need to, this is going to be very mechanical, very much a physics, much more of a physics process, because we're looking for forces. Okay, so to start, let's go ahead and have a system. Here is a cube of fluid. Okay, so this is somewhere inside this volume here. I've designated a very small cube. That dot in the center represents the center of this cube, and we'll say it's at z, at some height z. Okay, so this top surface has a height z plus delta z, and there's a pressure pushing down on that. Okay, because of our knowledge of buoyancy, the fluid above this is pushing down on it with some pressure. So there's a negative sign because it's pointing down. I've chosen up to be positive. So negative, this pressure, whatever it is, at z plus 1/2 dz, because that's the surface here. Okay, and then I multiply it by the area to get a force. So this area is dy dx. Okay, that's the two sides. And then this cube is being pushed from the bottom with the pressure at the bottom, z minus 1/2 dc. So this is the difference in pressure, and then this is the area of those faces giving me the net force. So this is the net force pushing up. Now, horizontally, there is no net force because they're at the same level in the bath, and so the pressure is constant all the way around at the same level. But there's a slight decrease in pressure at the top than at the bottom because of the height difference or the depth difference in the bath. Now, the question is, well, what if there's some other force? So for example, in this case, we could tell that there is a difference in pressure if an external force like gravity is acting on this volume of fluid. And so, but we could do other things. We could be pushing on it. It could be a horizontal tube, and so gravity's not an issue. We could be pushing on it with an external force. There could be an electrostatic force. There's just other forces that are actually pushing on this fluid. So the net force would be the force due to the pressure difference plus any other forces. Now in equilibrium, if it's not accelerating anywhere, particularly if it's not moving, then those should equal 0. So what we're going to do is we're going to say, let's instead of talking about the net force, let's talk about the force density. So that'd be the net force applied to this cube divided by the volume of this cube. Okay, we'll see that'll prove useful to think about. Now remember, dV the volume of this cube, is dx times dy times dz. Okay, so if I divide this side by dx, dy, dz, then for the pressure term, it'll cancel the dx, dy, leaving me with just a dz. And if I take this force to the other side and utilize that minus sign, so multiply everything by -1, then I have the force on the other side divided by dV. So this becomes the external force density divided by dV. But we've seen this now a couple times. This is a very common mathematical procedure to get to a derivative. So this is the definition of a derivative. P at a higher position minus P at a lower position, with that position being very small, and dividing by the difference in position. That is the definition of the derivative. So this is dP dz. So we can see that on this page. We have dP dz, and we define that external force per unit volume with this capital F. So this is a force density. Okay, and then so if we want to find the net force, we just multiply it by the volume of the substance, or the piece we're looking at. So for example, if this was a gravitational force, then our force would be mg, and we've got our dV there. That's a little volume, and mass is the same thing as the density times the volume. Volumes cancel, and we get a force density of rho times g. Okay, so that may not be familiar, but that would be, if you think of that, that's units of newtons per meter cubed. Okay, now if we plug that into this equation, dP dz equals rho g, and multiply the dz up and then integrate both sides, well, that's going to give us our familiar pressure equation, considering a depth alone. And so this checks out for that particular case, and we call that hydrostatic equilibrium. But I want to point out that this right here is any type of force. This could be a piston pushing, it could be an electrostatic force, any type of force divided by the volume. This is the particular case that we're familiar with, which checks out. Okay, so our goal is to try and utilize this idea and see if we can come up with the Van 't Hoff equation. This is a force idea. Can we come up with the Van 't Hoff equation thinking about a membrane, a semi-permeable membrane? So to get there, let's go ahead and talk about how does an external force, like this one, that acts on a particle, so like one of the solute molecules, how does it actually end up pulling on the fluid? So this is cool, because if that particle is moving and it's small enough, then we know that the net force is 0 because the drag force is so significant. We learned that back from the low Reynolds number world. So our external force is going to be proportional to our drag force, and that drag force is from the fluid, the viscosity of the fluid. So they're equal by the second law. But if the particle is pulling the fluid forward and the fluid is pulling back on the particle, that means the particle is pulling the fluid forward. Sorry, I said that backwards, which is a third law pair. Okay, so this is the force of the fluid on the particle. This is the force of the particle on the fluid. Okay, so since the external force on the particle is equal to the drag force, and the drag force is equal to the force on the fluid, then we know that the external force is equal to the force on the fluid. Okay, so with that in mind, now that we know that any external, so that allows us to maybe have charged particles and we can pull them with an electrostatic force, that's going to be that will be the external force that's pulling the fluid along. So back to our definition, we want to try and get this connected somehow to concentration, because we know that the pressure, the equilibrium pressure that we need to apply externally, which would be connected to this force, we saw that's related to concentration. So if this is the net external force acting on all the particles, and there are n particles, okay, or let's say dn particles in the little dV volume, if we say F sub P is the force per particle, then the net force on all the particles is equal to the force per particle times the number of particles. Okay, and we're talking about this small volume. So if the concentration is uniform enough in a volume, then in a certain region, I should say, then we can just say that dN over dV is the same thing as N over V. Okay, but this will be a function of position. All right, and so taking that, N over V is our concentration. So this is the force per particle times the concentration, which is a function of position. So plugging that into our previous equation that we have the derivative of P with respect to Z, or derivative of pressure with respect to Z, is equal to the concentration, which is also a function of Z, times the force per particle. But if that particle is feeling a force, we could also say that that particle has a potential energy with the external system, be it gravity, an electric field, whatever it is. And forces are related to the negative derivative of potential energy with respect to position. Okay, so that's nice. We have now pressure is related to concentration and a potential energy. Now that's exciting because we can take a pause here and say, I know how C and U are related because this is a thermal system, and so our concentration ought to be proportional to the Boltzmann factor, where the energy of question, the energy that's governing the distribution, is the potential energy. Okay? And so, this force, whatever it is, would want to pull the particles one way, but remember, thermal energy leads to diffusion, and so there's competing things. And so the stronger the force means the bigger this effect, but the ratio is what matters. So we already know by our diffusive environment, our thermal environment, that the concentration as a function of Z will be equal to some constant, and we'll talk about that in a minute. Some concentration at some point that we can say is a good reference point, times the Boltzmann factor. Okay. Now, if we take this, so we've got this this relationship, and we plug it in right there. So if we look at that, we can say that negative C du dt, since C is related to U, is actually equal to kBt dC dZ. Okay, now let's work that backwards just to make sure it's clear. What is the derivative of C with respect to Z? Knowing that the only place Z appears here is within U. U is a function of Z. So if I take the derivative of this, C is just a constant. Derivative of an exponential, you get the exponential back. Chain rule up into the power. And so the derivative of U with respect to Z would be a minus 1 over kBt. Okay, so that would come down as a negative 1 over kBt. And then the derivative of U with respect to Z. Okay, well, that left me with the C0 and the exponential. That's C. I get that back. You always will with an exponential. And then the chain rule gave me the du dz, which is right there. And I just realized I have a t here, which is not right. That was a little mistake on my part. Let me fix that here. That should be Z. I was going in autopilot on that one. Okay, so back to my hand. Okay, so that would have gotten me that, but remember, the chain rule pulled down a 1 over kBt, a negative 1 over kBt. The negative's good. I do need a negative sign, but I don't want the 1 over kBt. So if I multiply kBt times this derivative, then it will cancel the kBt that came out, and I am left with this correct form. So this equation here is equal to this. Now, I'm going to admit, I did a kind of a lot of speaking and pointing with this hand, where maybe showing those steps would have been good. But from what I just said, it'd be good for you to go check that. So pretty much take the derivative of C with respect to Z, knowing that U is the only thing that's a function of Z. Do your chain rule and show that this is equal to this, with C defined this way. So go and check that. I spoke through it, but go and check it to make sure it's clear. So, but with that being said, now I can say that dP dZ is equal to dC dZ with a coefficient of thermal energy. And that's a pretty cool relationship. And you're probably guessing now, well, I've got a 1 over dz and 1 over dz on both sides. So if I'm careful and consider my limits, I can end up, and you'll see it right here, I end up with the Van 't Hoff equation. Okay? But let's take a couple steps in between to make sure it's clear how we got the Van 't Hoff equation. Okay, so this is what we just arrived considering forces. Okay, we need to, let's go back. Where did the force come from and what range are we talking about? So here we have this semi-permeable membrane. Let's say that the concentration's on this side. Okay, this side there's 0 concentration, so I put 0C here. Okay, now what we think about is we say that on this side there's no force, nothing's happening over here. There's no particles over here, so there's no forces over here. And if you get really far away, well, there shouldn't be anything happening over here. The only thing that can happen is really right at the membrane. And what's happening is the molecules will diffuse around. They're just randomly diffusing around, and they hit the membrane, and they can't go that way. So it's perturbed diffusion. They will diffuse all over the place. If they end up hitting this, they bounce back. So there is a force. That is a force. Their momentum was this way, and it bounced. So the momentum's the other way, caused by this force. So this membrane, this physical membrane, pushed on them. And since it's impermeable, we can say that that force is effectively infinite, or better yet, the potential energy is infinite, okay, because it cannot get through. It cannot get through it. Okay, that's what the impermeable means. So if we were to plot that potential, we don't know quite what the function is, but it's going to be it's basically infinity at the wall, okay, and then it's going to get really small because there's really nothing happening out there. And I probably drew this not quick enough. It should decrease really fast and then come out to no forces. Okay, there's nothing in this region to push on anything. Okay, so what that's going to tell us is if our potential energy is really big here and gets down, that means there's not going to be very many particles over here because they're being pushed away. Now, it's a very narrow window. It's not very big at all. And so if you have a sharply decreasing function of u, whatever it is, and c is equal to the negative or exponential of the negative of that, then for very small values, it's kind of, it has a positive curvature, and it grows quickly and then levels out very quickly, okay, with that negative curvature. Okay, and if you're curious about that, I plotted it in Excel. I just selected a fastly decreasing function for potential energy. I did 1 over r squared, and then did concentration being equal to the exponential of that function, and just plotted it for a good range of values, and it gives graphs that look like this. Only it's quite sharp. It's quite sharp. So the point is that membrane is what's supplying the force. It means that far, far away, the concentration is at infinity. And so when we go back to our equation, this C0 is actually C infinity. It's just a constant. That 0 didn't mean at x equals 0. It just meant some initial value or some value, some constant multiplier. But it actually makes a little more sense now that if the potential is huge at the wall, big old force, then e to something huge, e to the negative something huge is pretty much 0, which means our concentration at z equals 0 is pretty much 0, which it should be, because they cannot get to the wall. Their centers, at least, cannot get to the wall because their edges bounce off of it. But far, far away, when z is huge, well, this is pretty much 0, and e to the 0 is 1, and I'm left with whatever concentration is far, far away. So that's why this is truly C infinity, whatever the concentration is far away from the wall. And so that's how we've got this concentration here, and I've written it up here too. So now that we know how to think about it, we know that there's whatever pressure on this side, whatever pressure really far away, a complex pressure in between, but it's pretty constant, fairly quickly going away. So if we integrate this, we can integrate both sides from really far this way to really far this way, then we're just going to get the delta P, because it's just a value here, so we get the delta P, and then we get this C, and if there's no concentration here, or we get a delta C, but if there's no concentration here, infinite concentration, or concentration at infinity over here, we just get that. Or if there was concentration on this side, let's say there's the same material but just less of it on this side, then it's just simply going to be a delta C, whatever that concentration difference is. Okay, now that was a lot, but the focus of what I'm saying is that we have recovered the Van Hoff equation, but we talked about forces this time. And that's what we really should think about. It is an entropic idea, but it's connected with forces. So without that membrane, there would be no osmosis. And to think a little more carefully about that, if you put a little blob of sugar, so I'm going to use an example of the text, if you put a little blob of sugar right here, it would start to diffuse, and there would be a concentration gradient, as it's diffusing. But there's not going to be any osmotic flow. The only time the osmotic flow happens is when you have this semi-permeable membrane, or a membrane that's impermeable to the solute, but water can flow through. Only in that case will you actually get a pressure difference and cause a flow. Okay? That's because as the molecules bounce, they hit that and bounce backward, and that pulls water through something we call entrainment. Okay, and I'll show a picture of that in a second. All right, let's move forward. Okay, actually I'm going to skip this and come back to it. So I want to talk about what that means here. So what's really important is that Van Hoff equation, which we're seeing right here. Okay, we're seeing here where that C0 is C infinity. That says that there's a pressure difference, but we need to reinterpret what that means. Okay. That pressure difference that would be created, that's the equilibrium pressure difference. Okay, that's what would be used to stop osmotic flow. So we would have to apply a pressure on this side that's bigger than the pressure on this side in order to keep nothing flowing through, because of this pressure change that we get due to the bouncing off the wall. So that Van Hoff equation, it describes, from a force perspective, it describes the pressure change here in this region. But what it also says is it's the pressure we'd need to apply over here versus the other side, so nothing flows. You notice through the membrane right here, this is a picture of the membrane from the text, through the membrane the pressure difference is 0 from here to here. That means there's going to be no tendency for water to flow through it. Okay, so we found that Van Hoff pressure as being this curve right here. Okay, this is how it works, and the only way that can happen is if we apply a pressure right here. So it's also the externally applied pressure which will stop flow. Okay, now what's cool is if you don't apply this pressure, so that both sides are at the same pressure. So for example, here's the one side pressure with the solute, here's the other side with the pure water. If they're at the same level, you still have this effect from the bouncing of the molecules off the wall, okay, which causes a pressure drop. So it's that Van Hoff pressure difference. And now, in order for this to line up from here, there's a lower pressure down here. And so fluid will flow across this pressure difference. It'll flow in the direction of the concentration. And so that is osmotic flow. So when it's not in equilibrium, where we're not applying an external pressure equal to this pressure drop here, okay, then you can get flow. And that will continue to happen until something happens like this. So this pressure will then rise up until it looks like this. So I guess a conclusion I would like to be clear, and hope that it makes it clear from the reading, is that this equation we found, you can look at it in one of two ways. One, it's the pressure drop in this region really near the membrane because the particles are pushed by the membrane. Okay? And in equilibrium, we apply externally that same pressure to stop the flow. But if we don't apply that pressure, then we will get flow across the membrane. So those are the two ideas there. Okay, now to conclude, we're going to talk about that flow in terms of volume flux of fluid. You know, how does the fluid actually go through? How much fluid? How can we describe it? Okay, and it's connected to some of the first things we drew about the second law and the third law and how viscous drag pulls. Okay, so to look at it, consider this as my membrane, a semi-permeable membrane. Water can flow through it either direction, but a solute particle cannot. So what this osmotic pressure is, it's really the membrane biasing the diffusion. So you can imagine a molecule here is just diffusing around under thermal energy, diffusing around, and it can go anywhere, but eventually it'll come and it'll approach this wall. But that wall says no, and it bounces off that wall. And as it bounces off that wall, it drags fluid through it. That's called entrainment, and that's because of that viscous drag we talked about, which is connected to the third law. Okay, so this wall effectively gives this net force because our position as a function of time was that way and then that way. That's a change in momentum, requires that force. And so our way to think about it is, well, how much fluid would pull through here? Okay, so that's going to depend on a few things. Okay, one, even if there is no solute over here, we could push fluid through here if we apply an external pressure. So no diffusive pressure at all, no entropic pressure, just a regular push of piston. So we could create this external force, create an external pressure, and we should get flow. Now, the flow will depend on how well the solvent can get through, and that is all encapsulated with this one coefficient called the filtration coefficient, called LP. And it depends on things like the fractional area of the holes, you know, how permeable is the membrane, as well as some chemical interactions. How does the chemistry of the membrane and the solvent, how does that work? That might be in a sense sticky, or there's attractive forces. Might be a little harder, or it's easy to get through. So we're not going to worry too much about all those principles, but you can measure that from looking at the flow rate and any mechanical things you do. So we can find out what that is. Then knowing that, and first of all, the minus sign in this case is because the flow is going to go towards negative or lower pressure. So the delta P here would have to be negative for our flow to happen. So that's if we had just pure solvent and we applied some external force. Well, our diffusive or entropic pressure, which is the Van 't Hoff equation, goes the other way. The fluid wants to flow towards higher concentration. So we have a minus and a minus. Okay, so this piece is what the osmosis does, the diffusion does, or the entropy does. And that's the piece we've been talking about mostly here. And so we can now describe the actual flow of volume if we, let's say we don't apply any external pressure. That would be the case I mentioned before, the bottom figure in the previous graph. And so we're going to get flow due to this pressure difference and no external pressure. But if we apply an external pressure that's equal to this, then we're going to get no flow, and that would be the middle picture from the textbook figure. Okay, so that hopefully will help. I know that was a little bit longer than I intended, but hopefully that'll help in reading in going over the readings. Pretty cool ideas about seeing how entropy and mechanics are related to each other.